The history of Mercury, the smallest and most hidden planet. Mercury is the first of our series of documentaries dedicated to the planets of the solar system, comprehensively describing their history and characteristics. It's the innermost planet of our solar system, so close to the Sun that it's almost always hidden in its blinding glare. We won't limit ourselves to describing the most well-known characteristics of this small planet. We'll go beyond, exploring its peculiar orbit that confirmed Einstein's theory of relativity, its strange relationship between day and year, its crater-riddled surface, and the surprising discoveries that continue to amaze astronomers. Comprehensive means exactly this: a detailed account, rich with information and insights that will lead you to see Mercury with new eyes, appreciating its complexity and hidden charm. Mercury is a planet of contrasts and mysteries. The first world of our solar system, so close to the Sun yet capable of hosting ice in its polar craters. So small it almost seems like a moon, yet so dense it harbors a disproportionately large metallic core. So slow in its rotation that a Mercurian day lasts 2 of its years, yet so quick in its orbit that it completes a full circuit around the Sun in just 88 Earth days. Its surface, marked by countless craters, is an open book on the evolution of the solar system, a cosmic archive etched in rock just waiting to be deciphered. But let's proceed in order and get to know this planet better through its numbers. With a diameter of just 4,879 kilometers or 3,032 miles, about 38.3% of Earth's, Mercury is the smallest planet in the solar system since Pluto was reclassified as a dwarf planet. Its mass is approximately 5.5% of Earth's, but despite its small size, its density is surprisingly high, 5.43 grams per cubic centimeter, or 338.4 pounds per cubic foot. Second only to our planet, suggesting a metallic core that occupies a full 60% of its total volume. Mercury orbits the Sun at an average distance of 57.9 million kilometers or 36 million miles, 0.39 astronomical units, completing a revolution in 88 Earth days. Its orbit is the most eccentric of all planets, with a value of 0.21 that varies its distance from the Sun from a minimum of 46 million kilometers or 28.6 million miles to a maximum of 70 million kilometers or 43.5 million miles. The planet rotates on its axis in 58.6 Earth days with an axial tilt of just 0.03 degrees, practically perpendicular to the orbital plane. The temperature on the surface varies dramatically from a scorching 427 degrees Celsius or 800 degrees Fahrenheit at the equator during the day to a frigid minus 173 degrees Celsius or minus 280 degrees Fahrenheit during the polar night, the most extreme temperature range in the entire solar system. The surface gravity is 0.38 times that of Earth. If you weigh 154 pounds on Earth, you would weigh just 58.5 pounds on Mercury. This cold, objective data doesn't tell the true story of this small, rocky world. However, its biography is literally written on its skin. Lacking a significant protective atmosphere and geological processes that continuously renew its surface, Mercury preserves, like scars, the traces of every cosmic encounter in its long existence. And the craters that dot its surface are testimony to a series of violent impacts that occurred about 3.9 billion years ago in a period known as the Late Heavy Bombardment. It's not easy to investigate the early phases of Mercury's life because it's the most hidden planet in the solar system. Studying it thoroughly, as we'll discuss later, is a challenge even with space-age technology. In the era when astronomers can only observe it with Earth-based telescopes, getting information about Mercury was almost impossible due to its position, being the innermost planet of the solar system. To see it from Earth, we're forced to look towards the Sun. Hidden in the Sun's glare like a frightened child, Mercury is difficult to see in the blinding light of our star and peeks out only occasionally for short periods. From our position, we see Mercury moving from one side of the Sun to the other as it orbits. For about a month, the planet is visible as an evening star at twilight, low on the horizon after sunset. For another month, it disappears in the Sun's glare. Then it becomes a morning star, visible before dawn for the next month. After that, it disappears for another month behind the Sun and finally returns to its initial position. It takes 116 days to complete this cycle. Initially, ancient Greek astronomers believed that Mercury's evening and morning appearances belonged to two different planets, which they called Apollo and Hermes. It seems the mathematician Pythagoras, around 500 BCE, realized that the two planets were actually one. He probably noticed they had a similar appearance, moved at the same speed, and crucially, whenever Apollo became visible, Hermes disappeared and vice versa. The name Hermes was the one that prevailed, so much so that even today in Greece the planet is called that. Elsewhere, the name Mercury spread, which was the Roman equivalent of the Greek god Hermes. Like all planets, Mercury follows an elliptical orbit around the Sun, which occupies one of the two foci of the ellipse. This geometry, so different from the perfect circle imagined by astronomers before Johannes Kepler, implies that the distance between the planet and our star varies continuously during its revolution. Like a pendulum that accelerates at the lowest point of its oscillation, Mercury also modifies its speed, faster when close to the Sun, slower when farther away. The parameter that measures this variation is called the eccentricity of the ellipse, and it's a number that ranges from 0 in the case of no variation, that is, if the orbit is in fact a perfect circle, to almost 1 if the ellipse has a long, narrow shape. The eccentricity of Earth's orbit, for example, is 0.017, almost circular. Mercury's eccentricity, however, is 0.2056, making it the planet with the most eccentric orbit of all. This means that its distance from the Sun is extremely variable, ranging from 46 to 70 million kilometers, or from about 1/3 to almost half the distance between Earth and the Sun. Early studies. First hypotheses. Due to the difficulties of observation, even in the telescopic era, Mercury remained for a long time a little studied planet. The first attempt to map its surface was toward the end of the 19th century. The Italian astronomer Giovanni Virginio Schiaparelli, the same one who observed the canals on Mars, who was also the first to hypothesize that Mercury's rotation period was equal to its revolution period, just under 88 Earth days. The work of mapping the planet was then continued and expanded by the Greek astronomer Eugene Michel Antonati, who in 1934 published the first detailed maps of its surface features. But to begin an in-depth understanding of the planet's morphology and internal structure, we had to wait until the second half of the last century, first with Earth-based radio and optical observations, then with space missions. The first important discovery was that, contrary to what Schiaparelli had initially proposed, the rotation period is not synchronous with the revolution period, but that the two are in 3:2 ratio. In other words, this means that the planet rotates on its axis 3 times for every 2 orbits around the Sun. The experimental data from the early 1960s provided by both Soviet and American radio observations was indeed about 59 days for the rotation period, compared to almost 88 for the revolution period. It was the Italian astronomer Giuseppe Bepi-Colombo who suggested that a 3:2 resonance between the two periods relative to the Sun was a stable solution, despite the astonishment of much of the astronomical community, convinced that the 1-to-1 resonance, synchrony between the two motions as observed for our Moon, was the more likely scenario. At the origin of this phenomena is the force of gravity that is exerted reciprocally between the celestial bodies involved, and in particular the tidal forces, which act differently between the different parts of the same body. For example, for Mercury, the greater attraction by the Sun of the hemisphere facing the star versus the lesser attraction felt by the opposite hemisphere. This action is always dissipative and slows down the rotation motion until it reaches an equilibrium solution, such as the 1-to-1 resonance for the Moon relative to Earth, or the 3-to-2 resonance of Mercury relative to the Sun. But be careful, all of this is not without consequences for the day-night cycle of the small planet. In practice, because of this very particular relationship between the rotation period and the revolution period, combined with the high eccentricity of the orbit, a potential Mercurian inhabitant would have to wait 176 days before seeing the Sun return to the same position in the sky. During the course of a Mercurian day, they would see the Sun rise in the east and advance very slowly across the sky, about 3 times slower than the sidereal motion of stars, increasingly growing in apparent diameter. Near the meridian, the Sun would slow down even more until it stopped completely. Then the Sun would perform a double reversal of motion before resuming its journey toward the western horizon, which it would reach 88 days later, returning to its original dimensions. Other observers, located at points with a different longitude, would see different but equally bizarre movements. At midday from certain longitudes, the Sun may appear 3 times as large as it does from Earth, and it is 7 times brighter. Nevertheless, the surrounding sky is black and star-speckled inasmuch as Mercury does not have an atmosphere in the traditional sense. It is a lonely sky without a satellite, nor even rings orbiting the planet. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You'll help us to make products of even higher quality. The surface. Are we on the moon? Mercury's surface appearance, well studied only following dedicated space explorations, is not very dissimilar from that of the moon, alternating between regions rich in craters and smoother, flatter areas that suggest past volcanic activity, like the one that gave rise to the lunar seas. On the other hand, the lack of an atmosphere causes the absence of erosive processes and surface features that can be preserved for billions of years. The structures that dominate Mercury's surface are impact craters. As on all other celestial bodies in the solar system with a solid crust, craters are of all sizes, and their topography depends on their diameter. Below 10 kilometers or 6.2 miles, there are only simple bowl-shaped craters. Between 10 and 130 kilometers or 6.2 and 80.8 miles, craters have a central peak. Between 130 and 310 kilometers or 80.8 and 192.6 miles, in addition to the peak, a central ring also appears. While beyond 310 kilometers in diameter, multiple rings appear. At equal diameter, Mercury's craters have an ejecta blanket that is 0.65 times smaller than that of lunar craters, probably an effect of the greater acceleration of gravity compared to the Moon. And then there are the smooth plains, which are the equivalent of the lunar Maria. About 40% of the hemisphere photographed by Mariner 10 is occupied by these plains, in 90% of cases associated with impact basins. From the analysis of the number of craters superimposed on the smooth plains, it can be deduced that these must have formed at the end of the primordial bombardment period, and their origin is probably volcanic. The intercrater plains, that is, those included between the craters, are more difficult to interpret than the smooth ones. On the lunar highlands, craters are so densely packed that they overlap each other. This is the phenomena of crater saturation. On Mercury, large portions of cratered surface are not saturated, and between one crater and another there is relatively flat terrain. Compared to the lunar highlands, craters with a diameter below 40 kilometers are scarcer in Mercury's plains. The distribution of intercrater plains and the lack of impact basins of which they could constitute the ejecta argue in favor of their volcanic origin. Another peculiar feature of Mercury's surface are the lobate scarps. These are abrupt crustal fractures ranging from 20 to 500 kilometers, or 12.4 to 310.7 miles in length, with heights between 100 and 3,000 meters, or 328 to 9,843 feet. The most notable of these structures is Discovery Rupes. In Latin, scarp is called rupes. There are few craters superimposed on the scarps, which therefore must have formed relatively late in the planet's history. In any case, only after the formation of the intercrater plains and the larger basins. The most plausible explanation for the formation of this system of fractures is that it is the result of the contraction of the planet's crust due to cooling. They would therefore be compression faults. A decrease in the planet's radius of just 2 kilometers or 1.2 miles is sufficient to account for the system of fractures that is observed. Nothing similar exists on the other terrestrial planets. In addition to the scarps, other elongated structures, the troughs, are also present on Mercury's surface. Troughs are structures a few hundred meters or several hundred feet deep, about 10 kilometers or 6.2 miles wide, and more than 100 kilometers or 62 miles long. Unlike scarps, troughs are aligned in three preferential directions: northeast, northwest, and north-south. The troughs form what is called Mercury's grid. Similar structures are also observed on the Moon and are attributed to the slowing of the planet's rotation period due to solar tides. Among the records cited earlier, Mercury also holds that of having one of the largest craters in the solar system in relation to the size of the planet that hosts it. The Caloris Basin, or Caloris Planitia, an impact crater almost 1,600 kilometers or 995 miles in diameter. Like the large lunar craters, Caloris Planitia is a lava plain and is surrounded by a ring of mountains up to 2,000 meters or 6,562 feet high. It is located at Mercury's equator, the hottest area of the planet, where the sun's rays are strongest. Not coincidentally, its name means plain of heat. Caloris Planitia was created by the impact of an asteroid about 100 kilometers or 62 miles in diameter, probably 10 times larger than the asteroid that caused the extinction of the dinosaurs on Earth. The impact was so violent, as evidenced by the crater walls, raised almost 2 kilometers or 1.2 miles above the surrounding terrain, that the effects propagated throughout the planet, generating seismic waves that traversed the entire planet, causing earthquakes at the diametrically opposite point, where a vast area called weird terrain formed. This region, characterized by a series of irregular hills and small craters with a conformation different from any other observed on the planet, was probably generated by the meeting of seismic waves that propagated on the planet following the impact, eventually breaking up and raising the previous terrain, although some hypothesize that it is made up of materials that fell back onto the planet's surface once they were lifted by the collision. Then the seismic waves returned, and the roar of the earthquake filled the planet, making it vibrate like a tuning fork for hours or perhaps days. The vibrations cracked Mercury's surface, from which incandescent lava began to emerge. Volcanic activity affected large areas, which were invaded by lava flows and transformed into smooth plains, the exact opposite of the chaotic terrain. The mountains trembled, landslides fell from their sides. The consequences of the impact extended to the entire planet. The formation of Caloris Planitia was a terrible event with global effects. The impact of the asteroid profoundly disrupted Mercury. If it had been larger, it would have literally torn the planet to pieces. The internal structure, the core, the magnetosphere, truly torn to pieces? Well, perhaps not. Mercury is in fact the planet with the highest density of iron, and it would therefore not be easy to reduce it to shreds. Nearly 3/4 of its diameter is occupied by a large ferrous core, 3,600 kilometers or 2,237 miles, compared to a total diameter of almost 4,900 kilometers or 3,032 miles. This core would occupy 40% of the planet's volume and would constitute a full 70% of its mass. In comparison, Earth's core is only 17% of our planet's volume. Proportionally, Mercury has the largest iron core of all the terrestrial planets. It's not easy to understand why, especially since theoretical models on the birth of the solar system predict lower densities. It's possible that the Sun, at the beginning of its existence, swept the innermost part of the solar nebula more energetically than predicted, allowing only heavy metals to aggregate. An alternative is the impact of Mercury with a large asteroid capable of removing the outer mantle while leaving the iron core intact. In this scenario, the impact would have occurred after the planet's differentiation. The rest of the planet is composed of a mantle and a crust made of materials similar to those of Earth's crust, especially silicon-based. Despite many thinking that Mercury's rotation was too slow for it to develop a magnetic field, the planet actually has one, dipolar and global, generated by a dynamo effect similar to that of Earth, due to the rotation of the planet's large liquid core. Although faint, its intensity is about 1% of Earth's. It is still intense enough to produce a magnetosphere and thus deflect much of the incoming solar wind. And the atmosphere? The planet's atmosphere, composed of hydrogen, helium, sodium, potassium, and calcium, is extremely rarefied, and therefore does not contain enough gas to reduce the heat and light it receives from the sun. Moreover, the slow rotation of the planet exposes different areas of the surface to direct sunlight for long periods. This leads to the highest temperature range among all the planets in the solar system. As we've already mentioned, Mercury's distance from the sun is highly variable, so the amount of light and heat reaching the planet can become at times more than double or less than half. Thus, the temperature also changes enormously depending on the time of day and the latitude considered. During the day, the surface temperature ranges from -183 degrees Celsius at the poles to 427 degrees Celsius at the equator. At night, heat disperses quickly from the bare rocks, and the surface temperature can drop to -200 degrees Celsius. At Mercury's equator, common metals like lead and tin would melt, and the plastic of a potential lander would end up melting or decomposing. Obviously, all this would be fatal for electronic instrumentation, with plastic-coated components, metal cables, and solders, unless adequate measures were taken to address the problem. So far, however, no one has found a practical solution. Mercury confirms general relativity. It's impossible to talk about Mercury without mentioning the fundamental contribution of this planet to the confirmation of the theory of general relativity. Observations show that every time it completes a circuit around the Sun, its elliptical orbit rotates in space, advancing the perihelion, that is, the point of maximum approach to the Sun. As we well know, Newton's theory of gravitation is extraordinarily precise in describing planetary orbits and the position of planets along their path. In the case of Mercury, however, it was noticed in the 19th century that the measurement becomes mysteriously imprecise. At the end of each circuit around the Sun, the planet was found to be in a position slightly different from that predicted by Newtonian calculations, and after a few decades, the differences accumulated, resulting in a significant deviation. Normally, as happens for all other planets, albeit to a much lesser extent, the major axis of the ellipse slowly rotates around the Sun, which is at one of the foci. This rotation of the orbit is called precession, and it is predicted by Newtonian theory. All planets, in fact, are characterized by this phenomenon, caused mainly by the gravitational attraction of other planets and especially that of the Sun. The precession speed can be calculated with Newton's theory of gravitation, which provides an almost exact answer for all planets except Mercury and Venus. During the 19th century, a precession of 5,600 arc-seconds, approximately 1.6 degrees per century, was measured for Mercury's orbit. However, calculations based on Newton's theory explained only 5,557 arc-seconds per century. What else was missing from the theoretical model to justify those missing 43 seconds? An arc-second is 1/3600th of a degree, so it's a minimal difference. But it couldn't be ignored, and it had become quite a headache for scientists of the time. Before having a satisfactory explanation, the French astronomer Urbain Le Verrier, the same one who had predicted the existence of Neptune, hypothesized that the anomaly was due to an as-yet unknown planet closer to the Sun than Mercury. This hypothetical planet named Vulcan was the object of an astronomical hunt that lasted decades, with alleged observations and denials, until in 1919, Albert Einstein offered an explanation. In his general relativity, gravity is an effect of the curvature of space-time, and a planet's orbit is not a static ellipse but would rotate anyway, even in the absence of the gravitational attraction of other planets. The closer to the Sun, the faster. And when he calculated Mercury's precession using his relativistic model, the German scientist astonished the scientific world by accounting for all 5,600 arc-seconds per century. The first space missions, Mariner 10 and Messenger. The proximity to the Sun, even in perspective, has always made the observation and study of this small planet very difficult, which has thus always remained on the margins of general attention, and partly also of scientific attention. For example, there are no photos of Mercury taken by the Hubble Space Telescope, which, to safeguard its sensors, has never pointed its photographic instrumentation in its direction, nor in that of Venus. And only 2 probes have visited Mercury, 3 with the recent Bepi Colombo still operational. It may be the closest of the planets, but it's also terribly difficult to reach. How come? Well, the problem is that heading towards Mercury also means plunging headlong into the Sun's gravitational well, which would attract the spacecraft to itself until it reached such a high speed as to prevent insertion into Mercury's orbit. The spacecraft would need to find a way to slow down, but this would mean carrying enormous amounts of fuel. The only other way is to slow down by relying on numerous gravitational assists with Venus and with Earth itself, with changes of course that, however, inevitably lead to greatly extending the duration of the journey. This explains the scant attention shown to the planet by the various space agencies. The first probe to visit Mercury was NASA's Mariner 10 in the first half of the 1970s, which took only 134 days to reach Mercury. The second was Messenger, with orbital insertion occurring in 2011 after a full 7 years of travel. The enormous disparity in flight times between the 2 missions depends on the fact that Mariner 10 limited itself to flying over the planet, without trying to orbit around it. It was attracted by the Sun's gravitational field and slowed down only by a flyby with Venus. It had a very rapid encounter with Mercury. Messenger's objective, on the other hand, was to orbit the planet, which it managed to do only after an infinite wandering between Venus and Earth in an attempt to dissipate energy and speed. Mariner 10, launched by NASA on November 3, 1973, to explore Venus and Mercury, was able, thanks to 3 close passes with the planet made between 1974 and 1975, to provide us for the first time with detailed images of its surface, as well as to discover the existence of the planetary magnetic field. Its most important record, however, is that of being the first probe to use the gravitational assist of a planet, Venus, to be directed towards another planet, Mercury. We recall that the slingshot effect consists of exploiting a planet's gravity during a close passage to accelerate or decelerate a probe, or even to modify its trajectory. Depending on the relative position of the orbits and the relative velocities, a probe can thus vary its orbital motion without using its engines, and therefore without consuming fuel, making possible trajectories and objectives otherwise impossible to reach for reasons of cost or time. And finally, 3 incredible facts. In 2008, the Messenger probe, launched in August of 2004, revealed that the planet possesses a long trail of sodium and calcium atoms extending over 2.5 million kilometers, or 1.55 million miles, into space. This phantasmagoric tail, invisible to the human eye but now detectable even with amateur instruments, is generated by the interaction between the solar wind and Mercury's tenuous exosphere. The charged particles of the Sun strike the planet's surface, causing atoms to jump, which are then pushed by the pressure of solar radiation, creating this extraordinary cosmic appendage. Like a planet playing at being a comet, Mercury reminds us that even the seemingly simplest celestial body can hold unexpected wonders. Like this other one we're about to tell you about. Well, believe it or not, despite what common sense tells us, it would be Mercury, not Venus, that is the closest planet to Earth. The relative position of the orbits is always as described in school books, but the distance separating the planets changes if calculated in relation to time. In practice, the orbits of Venus and Earth are separated by a distance of 0.28 astronomical units, while Mercury's orbit is 0.61 AU from Earth's orbit. Put this way, there would seem to be no doubt from a geometric and absolute point of view, Venus is indeed the planet that comes closest to Earth. But if the calculation is made with respect to time, that is, if one counts over a long enough period of time what the average distance of the 2 planets is, then it is discovered that Mercury spends a longer time in the vicinity of Earth than Venus does, so much so that the average Mercury-Earth distance in the long term is 1.04 AU, while that of Venus is 1.14 AU. It's a bit like what happens to us in everyday life. Between an uncle who comes to visit us once a year and then returns to his home 100 kilometers away, and the neighbor who lives all year round 100 meters from our house, who do you think is, on average, closer to us? Finally, one of the most poetic aspects of Mercury is related to the slowness with which the terminator, the line separating day from night, moves across its surface. Due to Mercury's peculiar rotation, so slow compared to its year, the terminator advances at a speed of just 3.6 kilometers per hour or 2.2 miles per hour, comparable to that of a person walking at a brisk pace. This means that a hypothetical Mercurian explorer could, in theory, walk along the terminator, remaining perpetually suspended between the scorching day and the freezing night, in an eternal twilight. Imagine being able to walk along the border between light and darkness, chasing a sunset that lasts for Earth decades, while behind you a dawn drags itself with the same indolence. On Mercury, this is not just a romantic dream, but a direct consequence of its orbital laws, a mathematical poetry written in the language of celestial physics.